This presentation is about levers. It is our final concept that we do need to cover for biomechanics. So the outcome is drawing to a close and we are starting to then change our focus in regards to preparing for the SAC. In regards to levers, things you need to be able to do, you need to be able to identify these different classes of levers. So there's 3 different categories that they can fall into. And each of those categories, you need to be able to draw a diagram that represents each one. So a very simple diagram. You can then be able to provide examples of each lever class and how they actually occur within the body, and also other examples of them that aren't necessarily within the human body. We're going to talk about this concept of mechanical advantage, and we'll look at that and how we actually use this to improve our performance in different sports. And we're also going to look at how levers can actually be manipulated to change our sporting performance. So to improve our outcomes, whether we're a beginner that's learning a skill or whether we are trying to get our maximal performance at the highest level. So some key terms I'm going to use throughout this presentation are force, axis resistance, and mechanical advantage. So these are terms that need to be used when discussing these concepts. And these are the ones specifically listed in the study design. So some information may have things like fulcrum instead of axis, but we're just going to stick to axis. And they might use terms like load as well, but we're going to stick to force. So using these key terms will be key to demonstrating your understanding of these concepts. To start with, got a short clip here about levers, or as the clip refers to them, levers. So levers, looking at the 3 classes and how they actually work within the human body, and then I'll talk about these concepts further.
Joints and levers in the human body. Objective: to understand how joints in the human body work as levers. A lever is a simple machine consisting of a rigid bar that rotates about a fulcrum and is used to transmit a force. There are 4 parts to a lever: lever arm, fulcrum, effort, and load. In the human body, bones act as lever arms, joints act as fulcrum,
or an axis,
and muscles provide the effort and force to move loads. Based on the arrangements of joints and muscles, different classes of levers are identified in the body. First-class levers have the fulcrum in the middle, like a seesaw. An example is the joint between the skull and the atlas vertebrae of the spine. The spine is the fulcrum across which muscles lift the head. Second-class levers have load in the middle, like a load in a wheelbarrow. An example is the heel joint. Here the upper body provides the resistance and the heel acts as the fulcrum. The effort is the contraction of the calf muscles. Third-class levers have the effort in the middle. An example is the elbow joint. When we lift a book, the elbow joint acts as a fulcrum across which the bicep muscle performs the work. Summary: joints and muscles in the human body function as levers. The joint between the skull and the first vertebrae is a first-class lever. The heel joint is a second-class lever. The elbow joint is a third-class lever.
Okay, so some of that terminology we'll look at and put into perspective in terms of the words that we need to be using in our study design. But that gives you a bit of a picture of what we're talking about when looking at levers in the body and how they actually create movement and those sorts of things. Okay, so the human body has levers all over it that help allow movement to occur. So they're things that when muscles work together with joints, we have movement, and that's because of this concept of levers. It is a simple machine. It has that rigid bar, so in the body, the bone acts as that rigid bar, and the joint forms the axis. So that video spoke about the fact that it was looking at the fulcrum, we're referring to it as an axis. And then the muscles contract and they apply a force that's overcoming a resistance, whether it's another part of the body that's forming that resistance, or whether it's an object that we are holding or an object that we are trying to kick or throw or whatever it is. So for a lever to move a resistance, so whether it's the bones or a ball or whatever it is, we must apply a force. And because of this concept, it allows us to have this thing called a mechanical advantage that we'll look at a bit later. So a mechanical advantage is something that allows a small force to create an ability to move a resistance that's greater than that. So we become more efficient at moving things because a small force put into moving an object can actually help us lift something that is quite much, a lot bigger, which is how we're able to, in day-to-day things, use, say, a wheelbarrow to carry lots of heavy objects in one thing. But if you were to try and hold that in your hands and try and move something, it would be quite difficult. So we'll look at this concept of mechanical advantage a bit later. So two main functions for levers. So if we're looking at levers in the body and how we use them in day-to-day lives, one function is to increase the size of the resistance that can be moved. Okay, so if we apply a particular force to an object, such as putting those objects in a wheelbarrow, we're actually able to overcome a greater resistance by lifting that wheelbarrow because of this concept of levers. Okay, so it allows this mechanical advantage that we'll talk about. The other thing that levers allow us to do is that we can actually increase the amount of velocity we can put onto an object. Okay, so if we take a golf club, for example, whilst the person swinging the golf club is having a certain amount of angular motion, because they have this longer lever, which is the club, the amount of angular velocity on the club head versus the person's hands is much greater. Okay, so it allows us to apply more velocity to an object, so therefore we can hit an object further. Whereas if we were trying to use a smaller object to hit that same ball, it wouldn't go as far because it doesn't have as much angular velocity on that club head. So all levers, they do have three parts to them, including that rigid bar that all of these things are balanced upon. So we have the axis, which is that pivot point, so it's where the movement's actually occurring. We then have the force, and that's what we're actually applying to move a resistance. So to move a particular object, we apply a force. And then the third part we've got is the resistance. So it's what needs to actually be moved. These three things combining together allows us to either increase the amount of force that we're able to apply to an object, or it allows us to add more speed and velocity to an object that we're trying to move. Okay, so there are three classes of levers. Okay, so, and their names are pretty easy: first class, second class, and third class. So pretty easy in terms of naming them. The challenge for some people will be actually trying to get the composition of these three components in the correct order, because each class of lever is structured in different ways, and that allows different advantages in terms of how they actually work and what they can do. So where they occur in the body determines what we can actually do with them. So some levers, such as third class levers, they're about being able to generate more speed or range of motion, whereas others, such as first and second class levers, they might be more about actually generating more force, so we can actually move a bigger object more efficiently. So you can see on the side of the screen we've got three different diagrams. So we've got our bar, a little triangle, and it's got a resistance, an axis, and a force. This is what I'm referring to when it comes to actually being able to draw what the each class of lever looks like. So we can see that our first class lever has the resistance, then an axis, and then a force. So that's our order for all first class levers. And then our second class levers, you can see that for this one, the resistance is now in the middle instead of the axis. And then our third class levers, we have the force in the middle. Okay, so pretty much we just move what's in the middle and that changes the composition of that lever. So I'll talk about each of these classes of levers. But what you need to remember is ARF. If you remember this order, so ARF, you'll be able to say that in a first class lever, the axis is in the middle. In a second class lever, the resistance is in the middle. And then in the third class lever, the force is in the middle. Okay, so that's how you're going to be able to remember the composition of these three classes of lever, so what their order is. And it doesn't matter with the first class lever if you put resistance on the left-hand side or the right-hand side. The only thing that matters is that axis is in the middle for that first class lever. So, talking about first class levers, as I said, the axis is in the middle, so it's between that force and the resistance. There's lots of examples of this, but they're not very common in terms of where they occur in the human body. Okay, so a crowbar is an example of a first class lever because the axis is where we're actually creating that movement. We are trying to overcome the resistance of whatever it is that we are trying to open, and then the force is applied by pushing down on that crowbar itself. You can see the seesaw example here. We've got our axis in the middle, so that's the kind of that tipping point for our seesaw. The resistance, we are trying to move that person that's at the bottom of the seesaw, that's down low. So they're the resistance that's acting down. And to be able to move that resistance, we must apply a force to that person that's higher up, and they will then be able to move the resistance. So it acts in that same sort of way. The video that was shown at the start, it talks about the head being a first class lever. So because our head sits on top of our C1 and C2 vertebrae, and our neck muscles actually pull back on the head, and that's how we actually create this lever, where the force is applied, the axis is in the middle, and the resistance is actually below that axis. So we're trying to overcome that, and that allows us to hold our head up. In terms of a couple of examples in sport, you can say a netball shot would be an example because that movement actually comes from the extension of the triceps. Okay, so if we use that, for example, the resistance is the netball that we're trying to overcome. The axis is that movement at the elbow, and the force is applied to that tricep muscle that allows that movement to occur. Another example would be a rowing oar. So you can see in this picture here, we've got a couple of rowers. What you might need to be able to do is identify what class of lever a picture is, and you do that by identifying, well, where's the axis, where's the force, and where's the resistance occurring. So in this example, our axis is in the middle because it is where the movement is occurring. So we can see that the hand actually moves backwards and forwards, and that movement is the axis. The resistance is actually when the oar hits the water. Okay, so we are trying to move, and so we are trying to overcome that resistance, and we actually apply the force at our shoulders. Okay, so we apply the force up here through our shoulders. So you can see that through this, we've got force on one side, resistance on the other, and our axis is actually central. And therefore that makes this a first class lever. So this is kind of the same as, say, a netball shot. If we look at throwing a ball as an example of first class lever, it must be an overhead throw, and it's purely movement through the elbow joint only. Okay, so a standard throw, we do lots of movement through our shoulder, so that changes it to a third class lever. But if it's purely just extension of the elbow that's creating movement to move that ball, it is actually a first class lever. Okay, so the axis is where that movement is occurring. The force is provided by that triceps muscle that actually extends the elbow joint and then overcomes the resistance of the ball to be able to create that movement of the ball. If we want to increase the amount of force that we apply to an object when we're using a first-class lever, we can either increase the distance from the axis to the force arm. So that point of movement, if you take a crowbar, for example, if you need to actually move an object that's quite heavy and has really big resistance, you use a longer crowbar, okay, because you're increasing the distance from the axis to where you're applying that force. Or you can increase the distance of the axis to the resistance. By changing this distance, it allows us to increase the speed in which we are applying that motion to the object that we're trying to move. So we have the potential to actually generate more force with less effort. Okay, so we don't necessarily have to apply more force to move the object. We just apply force over a greater period of time and increase that speed, so that allows that movement to occur. So people with longer arms, for example, they'll be able to move an object quite easily if they're doing an overhead throw, because they've got this mechanical advantage of having longer levers. A second-class lever, this is the resistance between the axis and the force. So that resistance is now the central piece. Again, this is one that's really uncommon in the human body. So we've got examples such as a wheelbarrow and a bottle opener that are in day-to-day life. But the main example that they talk about from a human body perspective would be standing on our toes. Okay, so if we take standing on our toes, we can see that the axis is where that point that's in contact with the ground. So where we actually stand on our tippy toes is that point. The resistance is the body weight pushing down, and the force is what's generated to actually bring the body upwards. Okay, so our wheelbarrow is an example of a second-class lever as well. The axis is that wheel. We can move that upwards and downwards. That's where the movement occurs. The resistance is acting downwards, and we pull up on the handles and apply that force to overcome the resistance. If we're looking at second-class levers, as I said, there's not very many examples in the human body, and that's because the body's just not designed to apply great forces through the use of levers. The way it's designed is actually about increasing the speed at which we can apply a force, and that's how we overcome the resistance to be able to create this mechanical advantage. So second-class levers, they're beneficial to help us increase the force output. So if we're looking at, say, heavier loads such as the entire body weight, and that we need to move the entire body weight, then we do use second-class levers, because it is really good at generating a big amount of force to move that resistance. Our most common lever in the body is a third-class lever. So 99% of the levers that we come across from a sporting perspective are in this category. And that's when the force is between the axis and the resistance. And this is because of the design of muscles. Okay, we know that muscles cross a joint, so therefore the force has to be in the middle. Examples of third-class levers from a sporting perspective, things like kicking a ball, swinging a bat, lifting a weight, all of these things are third-class levers. And you can see this diagram here of lifting the weight, that our bicep muscle, even though it does physically look like it appears where the humerus is, and you would think that the axis is in the center with this movement, we know that the bicep actually crosses in onto and inserts on our ulna. Okay, so because it inserts on the other side of the joint, you can see that it actually applies that force to this middle. Okay, so it doesn't attach here, and therefore there would be no movement occurring. So we've got our axis, then our force, and then the resistance. Okay, so the force is in the middle of this this diagram, and that's the case with the majority of the joints in our body, that tendon crosses over a joint, and it actually applies a force to the other side of that joint than what you would think it does. So, as I said, an example is kicking the ball. That would be an example of a third-class lever. So again, you need to think about, well, where is the axis in this movement? Where is the force being generated and applied to? And what is the resistance that we're trying to overcome? And in this particular example, the axis is the knee joint. That tends to be the easy thing to identify. The force is actually being applied to the tibia. Okay, so it is being generated by our quadricep muscles, and that quadricep, it crosses over via the patellar tendon and inserts at the top of the tibia. Okay, so the force does get applied below the axis, which means that it is the central part of this lever system. And then the resistance is when we're actually making contact with that ball. Okay, so the resistance would be where that contact happens, and we apply a force to overcome that resistance, which creates that movement of the ball. Okay, so as this diagram shows you more clearly, you can see that that quadricep crosses over the knee, so therefore the point of insertion is where the force is actually applied. It's applied to the tibia. So when we actually extend our leg when kicking a ball, that ball is the resistance that we are trying to overcome as well. Okay, so this axis is at the knee joint, the force is the central part of this lever system, and the resistance is where we make contact with that ball and move it. Okay, so in human movement, generally the resistance is at the end of the lever. Okay, so if we're trying to pick something up, we're trying to throw something, hit something, the resistance is whatever it is we're trying to use to hit that object, kick that object, whatever it is. Okay, so it is always at the end of the lever. The axis of rotation is that joint that moves. This is what creates movement. And the force comes from that muscle that contracts. And we know that the muscle will cross a joint, and when it shortens, it creates that movement at that particular joint. Okay, so these levers, they generally require more force to move a resistance. So they're not as efficient as the other two setups in terms of our levers. So we need to produce more force to overcome the resistance, but we can generate more speed on that end of that lever. So that's how we get the advantage in this respect. So I'll talk about mechanical advantage of levers from an anatomy perspective. Again, it's another formula, but you don't need to be able to calculate anything. What you need to pretty much take from this is we calculate our mechanical advantage by going the length of the force arm divided by the length of the resistance arm. Okay, so if the resistance arm is bigger than the force arm, then we have a mechanical advantage of less than 1. Okay, so if the resistance arm is less than the force arm, then we have a mechanical advantage that's greater than 1. And I'll talk about the consequence of those things in a moment. So the example that's in this diagram here is looking at a second class lever. So the resistance arm in this example is 2 meters, whereas the force arm is 3 meters. So if we go 3 divided by 2, we're looking at a mechanical advantage of 1.5. So in that particular example, it's greater than 1. So it's going to mean there's less effort required to move a resistance. Okay, so the force that's needed to move that load is less than the force that's being produced by that resistance. Okay, so that's why we're able to, for example, with a wheelbarrow, carry a heavier load, is because of things like if we have longer handles on that wheelbarrow, it can be easier to actually move that resistance. Okay, because we have this greater mechanical advantage. If the mechanical advantage is less than 1, which is usually the case in third class levers, it means that we're actually able to increase the range of motion that's possible at that lever and have more angular speed that can be produced, but we need to actually create more effort to move the resistance. Okay, so this is why we don't have ridiculously long golf clubs that are just too big to actually move, because the effort to actually move that club and generate some movement on that club would be too great. Okay, because we would not have this mechanical advantage. Okay, so there's that trade-off between, well, if we increase the length of the force arm, then that's going to allow us to generate a greater force to overcome that resistance. But if that force arm is too long, then and the resistance arm is even bigger, that's going to lead to issues in terms of trying to generate enough effort to overcome that resistance. Okay, but on the plus side, if our mechanical advantage is less than 1, it's going to help with things generating angular speed, which we can then put onto the object we're hitting, for example. Okay, so an example of this, if we're looking at 2 different length levers of the same object in this baseball example, if we are hitting the ball at the S1 spot, our swing, there's not going to be much angular velocity happening at that point. Okay, so we wouldn't be able to then transfer that velocity onto the ball that we're trying to hit. If we then were able to hit S2, so further down the bat, there's more velocity at that point on the bat. It's traveling at faster speeds compared to closer to the axis. Okay, so that's going to allow us to put more velocity onto the end of that object. So the further that point is from a lever, the greater the velocity of that lever that's moving through the air. So this is why, if we're doing lacrosse, if you're trying to do a long pass, you actually put your hands right down the bottom of the stick and try and fling it that sort of way, and that can generate a lot of velocity on that ball, and that gets, when it goes through the air, that gets transferred into that ball traveling through the air. The issue with that is then we have issues with accuracy and more skill error and those sorts of things. It's also the reason why things like kids' rackets for different sports, they tend to be smaller. Okay, so they can actually, they don't have to generate as much force to be able to swing that object because of this principle of leverage. So if we look at these anatomical levers in the body and we try and make them bigger, so we use a longer racket or a longer club, or we actually stretch and extend our arms out, those sorts of things, it does increase the distance from the axis to the resistance. And that means that we're going to have a resistance arm that is greater than the force arm, which means there's not going to be that mechanical advantage. So we actually need more force to swing that bat. Okay, so if you have your hand really close to your shoulder and you try and swing it, you don't need to generate much force to be able to get that movement happening. But if you stretch your hand out, you have to generate more force to move your arm to be able to do that same sort of movement. Okay, because we lose that mechanical advantage. But if we also extend, if we look at the positive of this situation where you use a longer racket or you stretch out your hand further, you have a greater range of motion. So you can get more velocity at the end of that lever, and that can result in a ball being thrown or hit or kicked further. So that's why we do things like stretch our leg when we're kicking the ball, for example. So with this understanding of levers, we need to look at, well, how can that knowledge of levers improve performance in these 4 sports listed above? So how can we manipulate this concept of levers to improve our ability in golf? So, because different clubs are different lengths and they produce different distance shots. Tennis, how can it impact on our serving? Soccer, looking at how it can impact on how we kick the ball. And baseball, how does that impact on hitting? So in relation to golf, you can see in this diagram of the different golf clubs, they're different length golf clubs. So the shorter ones, we actually use those clubs for shorter shots. Okay, and that's because they actually have a lower lever length. So we can still put a full swing shot onto that golf club, but it's not going to travel as far then putting that same swing on a longer club. And that's because of this lever length. Okay, we can generate more angular velocity at the end of these driver clubs, so these ones that are to the right of the picture, and therefore there's more club head velocity that gets imparted onto the ball when we hit it, so the ball goes further. If we take tennis, for example, when we serve, we try and extend our arm as much as we can at that point of impact so that we can produce more racket head velocity, and that means we have a faster serve. So if you watch tennis, you'll see tennis players on their first serve, they'll put everything into it and they stretch really high, they have a higher ball toss, all of these sorts of things to try and really extend their lever. If they make a fault on that first serve, you'll see their techniques changes just slightly. They reduce that lever arm length. So it's not necessarily as fast, that serve, and it can then help with things like accuracy to make sure they get that second serve in. In terms of kicking a ball, okay, so if you try to kick a soccer ball or a football as far as possible, you fully extend your leg at that point of impact, and that's going to allow for maximum distance in the kick, okay, because that's that point where it's extended, it's got the longest lever, there's the most angular velocity on the leg as it's coming through and making contact with that ball. In baseball, the batter should grip the bat at the end to make that bat as long as possible when trying to hit a home run. And then on the flip side, when they're trying to do a bunt ball that just drops very short, they will choke the bat. So they'll bring their bat, they'll change the grip and shorten the grip so that it's closer to the other end. So they make the bat shorter. In regards to equipment in different sports, so an example being children in sport, we modify their equipment to make it smaller and lighter. Okay, so if we gave a kid that's just starting in tennis a full-size tennis racket, it's probably going to be just as big as them, and it's going to be too difficult for them to swing because it's too heavy, and the length of the racket is going to be too long. So they'll actually have issues because the moment of inertia of that tennis racket when they're trying to rotate it through their swing will be too great. So there's too much inertia that they need to try and overcome, and they can't physically do that. If you give a kid a tennis racket and it's too big for them, they'll automatically grip it closer to the head of the racket. Okay, so rather than actually gripping it down here on the proper grip, they'll be gripping it up in this area. Okay, and automatically, without even knowing what they're doing, they're decreasing the length of that lever. Okay, and that's going to help with decreasing the moment of inertia, and it's going to help with making it easier for them to swing that tennis racket. So therefore, they're going to learn good technique, and then they can start to build on it and gradually increase the length of their rackets as they progress. Juniors, when they start to play tennis, their serve, they'll often serve from the wrist or the elbow rather than serving mainly with their shoulder. And again, that's just shortening the lever, so they don't need to generate as much force to be able to create that movement. Okay, they haven't developed that strength to be able to generate enough force to overcome the resistance of what they're trying to do. So you can see with this stuff that textbook, it just loves tennis as an example. And the VCRA exam, they love tennis because they write the exam between November and April, and the Australian Open is on during that time. And a good example of levers in tennis and how people use it to their advantage would be an Australian tennis player. He's just retired, Sam Groth. Okay, he's quite tall for a tennis player. So be looking at 6'4" in terms of his height, and he's got the world record for the fastest recorded serve in tennis. So on average, your male tennis players, they're looking around their top speeds being around 220 kilometres an hour. And Grothy, he hit 263 k's an hour in a game. Okay, and he did this because if you can see how much he's extending his body and increasing the length of his lever arms. Okay, so that's going to allow him to put more velocity on the racket head as it's traveling through the air, which then, when it makes contact with the ball, all of that velocity gets transferred into the ball, which is why it travels so fast at that top speed. So all of the tennis players that are in the record books for the fastest serves that have been on record, they're all over 6 foot tall. Okay, they're massive servers and they use levers to their advantage. Okay, they're able to generate that velocity on the tennis racket, which gets put into the tennis ball, and that tennis ball travels at a greater velocity through the air. Okay, so in Sam's case, it was 263 kilometres an hour, the fastest serve that's ever been recorded, because he is quite tall for a tennis player. So a summary of our levers. This is a good summary table that your textbook has that really succinctly describes all of these things and what you should know about each of these levers. So for first class levers, obviously you've got your drawing there that you need to know, so that our first class levers, the axis is in the middle. With the direction of force versus resistance, in a first class lever, both of them act downwards, so in the same direction. Okay, if we're looking at mechanical advantages, that's going to allow whether we're able to generate more force or generate more velocity on that object. And this table's good because it gives you a practical example, so it's quite easy for you to see, for example, that a seesaw is a good example of a first-class lever. But it also gives you a human body example because the study design specifically says it's in relation to human movement that we're looking at these concepts. Okay, so making sure that you know that if we're looking at a first-class lever, we're talking about overhead elbow extension or extending our head, so lifting our head up. Our second-class levers, we're talking about standing on our toes. And then third-class levers, the easy ones, talking about flexing the elbow, but extending the knee, extending the hip, all of these sorts of things are examples of third-class levers. So your textbook's got a couple of questions there that give you a bit of a practice at explaining these concepts. And you've got chapter review questions there that will help you as well. So that's the end of the presentation. I will look at these concepts again on Thursday in a bit of a prac session, so we'll look at manipulating levers. So make sure you go through this again, and if you've got any questions you need to ask me, have them ready for me on Thursday.